Congratulations, cadets. You've been accepted to Sidwell Space School. My name is Nico Rose.
And I am Robert Foster.
Today, we are going to be covering special relativity, a critical subject for any space cadet. Before we begin, you should know relativity puns are acceptable at any point in space-time.
Now, we are going to recount several of our relatively interesting adventures in an effort to educate you cadets.
First, we will introduce your minds to the concept of reference frames, which is relatively essential to your understanding of special relativity, with an experience of ours.
One day, we left our space cubicles to go for a casual moonwalk together. We looked up and saw two spaceships traveling in opposite directions. The first ship, we'll call it Ship A, was going 50 miles per hour, while the second, Ship B, was going 100.
To us, we stayed put while the others moved at their respective speeds. However, to the driver of Ship A, we were zooming by at 50 miles per hour, and Ship B was going 150 miles per hour.
Each perspective in this situation is its own reference frame, and the speed of each object varies depending on which one you take. Also, each reference frame has 4 dimensions: x, y, z, like a regular 3-dimensional coordinate plane, with the 4th dimension as time.
Now, after you've learned about reference frames, you may be curious what makes special relativity so special.
In special relativity, we only deal with reference frames moving at constant velocities relative to each other. A very smart man named Albert Einstein came up with 2 very important postulates, or laws, about the speed of light in reference frames, called Einstein's postulates.
The first postulate says that in all inertial reference frames, the laws of physics, including Newton's laws, are the same. Also, every reference frame going at a constant velocity relative to another inertial reference frame, never changing speeds, is also an inertial reference frame.
The second postulate states that the speed of light is the same in every reference frame, as long as both frames are moving at constant velocities in a vacuum.
After you've learned about Einstein's postulates, you cadets are now relatively ready to know about the Lorentz transformation formulas. But before that, let's learn about an assumption that physicists before Einstein made.
Before Einstein, many physicists assumed that time was the same in every reference frame. To put it another way, all standard clocks could be synchronized, no matter the frame of reference which moves with it.
This may be what we observe on Earth, but when we go really, really fast, this assumption no longer holds.
With some relatively simple math, Hendrik Lorentz came up with equations to express the position and time functions of a reference frame in terms of the position and time functions in another reference frame moving at a constant velocity relative to the first reference frame.
From these Lorentz transformations, an invariant expression can be derived in terms of space and time. This is an expression in terms of space and time that is the same for an object from any viewer moving at a constant velocity relative to each other.
Now, let's recount our experience in a spaceship dealing with time dilation and length contraction.
Where are we?
We are in the Star Fox spacecraft during the summertime, going 999,999,999 billionths of the speed of light. We're trying to make summer go by faster for us, and not arrive at school late.
Why are we trying to skip summer?
Because we love school so much. Now, let's calculate how much time we should spend in this spaceship before arriving at school for 9th grade. We wouldn't follow Earth time, but we have to consider time dilation.
Referring to the handy invariant expressions, I can find that one Earth day goes by in about 3.86 seconds in this spaceship. So, if there are 104 days of summer vacation, we need to spend only about 6 minutes and 41 seconds going at this speed according to our space clocks.
Indeed, a masterful plan. Here's a more intuitive way to think about time dilation. Suppose our spaceship and one of our relatives, say good ol' Aunt Betsy, starts out exactly where we are. Aunt Betsy somehow travels at the speed of light, and we travel slower than her in the same direction. You would expect that relative to our spaceship, Aunt Betsy is traveling a bit slower than the speed of light.
However, Einstein's postulate says that the speed of light has the same value in every reference frame. So, something's wrong. From math class, we know that distance equals speed multiplied by time. The only way to make the equation correct is to change the time and distance. Thus, we have time dilation.
Hold up. You said that distance also changes?
Why, yes, I did. This is called length contraction. Let's do a quick demonstration of this. Here, I have a standard meter stick from Earth. My relative on Earth, Uncle Jerry, has an exact copy of our meter stick.
Uncle Jerry happens to have insanely good eyesight, so at exactly 12 Newton, he will measure what the exact distance between the endpoints of our meter stick is in the units of his meter stick.
Robert also happens to have insanely good eyesight. So, at that time, Robert will also measure the length of Uncle Jerry's meter stick from space with respect to our meter stick. Please note that Robert and Uncle Jerry will not take into consideration the distance between our meter sticks in determining how long they are.
Okay, 12 Newton Uncle Jerry's time is approaching in 3, 2, 1... I measured that Uncle Jerry's meter stick is about 44.7 micrometers in terms of our meter stick.
Wow, that's really small. The results are in from Uncle Jerry. He measured, drumroll please, about 44.7 micrometers.
What? How is that possible?
Well, from each of our respective reference frames, the other is going really fast and shrinking. The same doesn't go for time dilation because one is going faster through time while the other is going slower. We can now study what a lot of people instantly associate with Einstein, E equals mc squared. If you don't know already, E equals mc squared represents energy equals the mass at rest times the speed of light squared.
Here is the derivation of E equals mc squared.
What you should know about E equals mc squared is that it is an equation to calculate the energy of an object at rest. The term at rest means the object's center of mass is stationary in an inertial reference frame.
The equation is very useful in solving problems involving particle decay. In particle decay, you will see that some mass gets converted into energy.
For example, an alpha particle has less mass than the sum of the masses of 2 protons and 2 neutrons. The extra mass comes from the energy of the strong force when the alpha particle is taken apart. That amount of energy is calculated by E equals mc squared.
However, E equals mc squared is just a specific form of this equation, though this is just E equals mrel c squared, where mrel is the relativistic mass. Notice that as the velocity approaches the speed of light, the energy diverges to infinity.
Also, don't try to go past the speed of light. It's impossible. Robert and I have tried it once. It was terrible.
Oh no, not that time. Now, are you ready to learn about the one thing you should remember from special relativity?
The most important fact of the universe?
The thing that will keep you alive in space?
The most important fact you will ever learn about the universe is...